Hello, ladies and gentlemen. Today we're going to be talking about series and parallel circuits. What I'm going to do, I've got a really unique website that's got a lot of interactive simulations. It's phet.colorado.edu. And you go into these simulations here, and you go to physics, then you come down to, let's see here, electricity and magnets and circuits. And it's going to be this one right here. It's the Circuit Kit Direct Current Only. It's this one right here, Circuit Construction Kit DC Only. Now I've already set this up and I've got some stuff built here. And here I've got a switch that I can actually turn on a light bulb. So here's a light bulb and I've got an ammeter already built into this. So I can open up, this is called a knife switch, so I can close the switch, open the switch, close it. And I want you to notice, so here's the light bulb. It provides a certain amount of resistance, and I've got a certain amount of current flowing through it, and there's a certain amount of pressure. And I can check all these things. I can grab myself a voltmeter down here, and I'll put right here my black, and I'll put right here my red, and you can see that I screwed it up because it's negative 9 volts, so this one must be the negative, this one must be the positive. So I've got 9 volts. So this is a 9 volt battery, and there's 0.9 amps flowing through here. So you could do a little bit of math. 9 divided by 0.9 is going to be 10. So this has an approximate resistance of 10 ohms. So here's what we're going to do. I'm going to explore what's called series and parallel. Down here I have the same thing. All three of these circuits are exactly identical, but I've set them up to hook up multiple light bulbs. So in a series circuit, what I'm going to do, I'm going to hook up 2 more light bulbs in what's called a series connection. And over here, I'm going to hook up 2 more light bulbs in what's called a parallel connection. And I want you to see what's similar about them, what's different about them, just so you can see. I thought this was a really cool visualization that shows us how this really works. So here, let's look at my series connection first. So I'm going to turn my circuit off. I'll turn this one off too. So I'm going to break this circuit right here, split the junction, and I'm going to take this wire to this light bulb, and then I'll hook up another light bulb and watch. Do you see a difference? Look at the difference in relative brightness, first of all. You can see that this is not as bright as that. Look at the current. I'm getting half as much current because I've added another kink to the hose. You can think of this like a hose. You kink it here and then you kink it there. The more places that you add kinks, that you're limiting how much current flows through the entire hose. Now I can do the same thing again. I can add another light bulb to it. So I'll hook it up to this light bulb, hook this wire up to the battery, pull it down here, and you'll notice that every time the current is going down. So I'm going to bring over this, it's called a non-contact ammeter. All I have to do is move this little crosshairs and it will tell me how much current is flowing. And you can see that there's 0.30 amps going through this wire. And if I come up here, the same amount. If I come over here, the same amount. If I come over here, the same amount. Everywhere I put this ammeter, where I measure the current, it's always the same. So that's an important understanding of a series circuit, is that the current everywhere is the same. So a series circuit is chaining. It's chaining together devices like a train. Like you hook one thing into the next, which goes to the next, which goes to the next. The current is the same. The current is the same everywhere. Now along with that, like let's say one of my light bulbs becomes disconnected. Notice how the current stops everywhere. Maybe some of you have had this with some of the older Christmas lights where if one light bulb goes out, the whole string goes out. That's because it's a series connection. Because that filament that's inside of this light bulb, if that burns and melts, you're literally breaking the circuit and no current can flow through anywhere. You replace the light bulb, you have current going through there again. Now let's take a look at the voltage. So I'm going to bring my voltmeter over here again. And I've still got, if I look at my battery, I think it's the same battery, 9 volts. It's a 9-volt battery. And we can look at the voltage around the switch. We should get 0 because there's no kink there, so there should be no, we shouldn't get a voltage around the ammeter either, because ammeters are just supposed to let the current travel straight through with no impingement. Now the light bulb, I've pinched it once right here, and you'll notice that it's 3 volts. Let's look at the voltage across this next one. 3 volts. Let's look at the voltage across the third one. 3 volts. So the voltage adds up to the total. So if you're thinking about this in terms of pressure, like how hard you're pushing the electrons through, if you kink the pipe in 3 different spots, the pressure buildup over all 3 kinks is exactly the same. Now, I think let's try to, what I'm going to do, I'm going to replace this light bulb with a resistor, because these light bulbs, they have the same resistance. What if they had different resistances? How would that work? You'll notice that there's 3 volts across each one of these. What if they were different? So I've removed my light bulb, and here I'm going to grab a resistor, pull my resistor over here, insert it into the circuit, and let's see what happens. I get the same current. So this resistor must be the exact same resistance. So let's right-click on this, and it says show value, 10 ohms. What I'm going to do, I'm going to change my resistance. Let's make this, let's double it. Let's make it 20 ohms. You'll notice that my current went down because I've added more resistance, and you can see that the relative speed at which the water is flowing, that's current, how much water you were getting per second, compared to my original circuit up here. And let's look at the voltage now. The voltage here is 4.5 volts. I've got a 4.5 volts here. Let's look at the voltage across this light bulb. 2.25. And let's look at the voltage here. 2.25. So if you add those all together, 4.5 plus 2.25 plus 2.25, you get the total voltage, which is 9 volts. So that's another important essential understanding for a series circuit. The voltage across all components adds up. Now let's look at a parallel circuit. So I've got a parallel circuit over here. I'll shut this one off. Here's the difference between a parallel circuit. I'll turn this circuit on, and you'll notice it's the same one. Now what I'm going to do is I'm going to add another light bulb like this. See what I did right there? If I can, I added another light bulb in parallel. A parallel circuit is where there's a choice. You've got electricity flowing, and it gets to this point right here. We call this a junction or a node, and it can choose a path. Current goes to the right and current goes to the left through both light bulbs equally. Because they have the same resistance, the same amount of current is flowing through each one. And I'll bring out my non-contact ammeter again. And you can see right here, I have 1.80 amps flowing through this branch. And if you look right there, I have 0.9 amps. 0.9 amps. So you'll notice that the current is going across here and the current splits. Half of the current goes down and the other half goes through the other one. Now what if I take this away? What if I change the resistor here? So what if I make a bigger resistor? So I'll split that right there, and I'll have to split this junction. I'll take away my light bulb. I'll put in a resistor. And let's put my resistor here. And I'm going to change it so that it's twice the value. So I'm going to make it 20 ohms. here you could see, maybe I'll make it even bigger. Maybe I'll make it 50 ohms. Maybe I'll make it 40 ohms. So you can see the current splits, but look how much current is flowing through this branch compared to this branch. There's less resistance by the light bulb than there is by the resistor. So more current is going to flow through here, but the current is still going to add up. I go back to my non-contact ammeter. So let's measure. I got 1.12 amps, should be flowing through here. And then I've got 0.22 amps, and then this should be 0.90. So 0.9 plus 0.22 is going to equal my full current. So that's an important understanding with a parallel circuit, is that the current adds up to the total current. So in a parallel circuit, it's like we're adding extra pathways. I can keep adding more and more pathways, and I can pull more and more current. So the current through all the components or all the pathways adds up. And then the voltage is the same everywhere. So this is, the series and parallel are are complete opposites. In the series circuit, the current is the same. In a parallel circuit, the current adds up. In a series circuit, the voltage adds up. In a parallel circuit, the voltage is the same. So here, I'll add another light bulb to my mix here. Watch what happens to the current. It goes up. The more and more things I add, the more pathways I add, the bigger. I'll put my other light bulb back in here. I can continue to add more objects, and you'll notice my current gets bigger and bigger and bigger. And this is where circuit breakers come into play. Your house is designed to protect itself. If you plug in your iron, you plug in your toaster, you plug in your refrigerator, you plug in your TV, you keep plugging things in. Turn this lamp on, turn that clock on, turn the stereo on. The wires in your house, look at these wires right here, are carrying the full load, and they will melt and they can start fires in your walls. So we design what's called a circuit breaker, that when the current reaches a certain amount, it trips this breaker and doesn't allow any more current to flow. And you'll notice, you see how slow it moves through this branch, and then when this branch meets this branch, these two pile up and they have more currents. So when I go to my non-contact, notice that there's 0.9 amps, just like my original circuit over here. So 0.9 plus 0.9, in this right here, this should be 1.8 amps, and it is. So I add another 0.9 to that, and that would be 2.7 amps. So in this wire right here, it's carrying the full load, as is this one. All those currents add up. Now, the benefit to a parallel is, what if one of these comes detached? Like, what if one of your light bulbs burns out, or for instance, you'll notice that the other two light bulbs can stay going. So newer strings of Christmas lights, if one goes out, they don't all go out because these are wired in parallel. Same with your house. You don't have to have something plugged into every single outlet in order to get them all to work. Imagine how funny that would be, that you had to have something plugged in everywhere to get everything to work. No, we've got things. This is what a plug-in looks like, literally. This is the plug-in in your house. This is wiring of your house. There's a plug that's waiting for you to put something in there, be it a television, and anything you plug in, a cell phone charger, touches that, starts drawing current from your main going through a breaker in through each room. So this is the fundamental difference between series and parallel. I encourage you to go on this website to check it out, to see how this all works, and just remember that you chain them together like a train. That's a series. The current is the same everywhere, but the voltage adds up. In a parallel, you're adding different pathways. The current is different, but the voltage is all the same. And along with the voltage being the same, I just wanted to show you that, because I didn't really show you that the voltage across each one of these is all going to be 9 volts. So here I get -9. I'll make it the correct orientation. Here's +9. And I go over this one and I get 9 volts. Because this battery is able to push evenly across all of them. Like it's pushing. It's like people trying to leave a gymnasium. You open up doors, everybody pushes equally, but whatever door has a larger width, more people are going to go through. So if you've got one of these things as it's easier to get through, it has less resistance, more current is going to flow through it. So the pressure is the same across all of these resistors, but the amount of current that flows through it depends on how big that resistor is.